Hey, what's up, guys? Chung here. Okay, so today, let's talk about another uh, dynamic programming problem, number 403, frog jump. Yeah, I think I like this problem, so I'm gonna give my own vote here. So, a frog is crossing a river, and there are like a bunch of stones, right, separated across the river, and the value on the stone represents the distance basically from the left bank, right, to the yeah. Basically, this stone has distance 1 to the left bank, and this one has 3, this one has 5, this one has 6, right, so on and so forth. And a frog always starts from the stone 0, and then you you need to write a program to determine if this frog can jump to the last stone, which is 17. hmm And the way the frog jumps is it can only jump, assuming the last jump was k unit, or the k distance, right? And the next jump must be either basically the has to be like in the range of k minus 1 to k plus 1, right? For example, if the last jump is 4, right? Then the next jump can only jump 3, 4, and 5. That's the range for the next jump. And you need to write a program to see if this frog can jump to this 17 here, right? So I think it's obviously a dynamic programming problem, but how how do we conduct our solution, right? And I think one way is that we need to know, for example, let's define a DPI here, right? Let's define a DPI here. So the normal way of thinking about dynamic programming, we need to deduce the value of DPI from something DPI minus one, right? Or DPI minus two, something like that, right? And if we go that route, this problem can be solved. So basically, this DPI and J, right? So this I means the ice position of the stones, right? And then what do we do? And the key is the stone index, and the value. What's the value? The value is gonna be the key is the stone, right? And what's the value? The value is a set. It's a set of all the possible jump distances that can reach the current stones, right? Set of all jump, right? For example, if there are like 3 ways that can reach this DP, right? So they're gonna be have three sets in the V here. Like for example, 3, 5, or 7, right? And every time when we see this DPI here, right, we just loop everything starting from 0 to I, right? And for each of the DPK, right? For example, of a K here, if each of a DPK here, we check, okay, among all the for all the Ks, right? For each like the jump options from this DPK, if this thing is in the range of I minus K, right? Because if the current I to current K, that's the distance of IK, right? If this IK can be jumped from any of these values, right? If it is, then we know from K to I, we gotta like we have a result, right? So basically we just add this from the distance, the jump I minus k to this current I here, to dpi here, and we just loop through all the possibilities from 0 to k, right? And in the end, we just check, okay, so if the dpi, the set in the of this dpn minus 1, right? dpn minus 1, that's our final result here. If this dpn minus 1, if the length, if the set, right? If the length of this, because the value of this is a set, if the length is greater than 0, then we know we have at least one possible ways of jumping into this the final stone, right? Yeah, that can be that I think that can pass, but it will be a bit slow because for each k, right, every time we do a we do a loop from 0 to I, right? So basically that will be like I think o n o n square, no, o n square times n, I think o n like to the 3. Yeah. Okay, and there is another way of thinking about this problem. I think that's the correct solution we're gonna based on today. We're gonna do it. That's the correct solution we'll be coding on today. So okay, let me clear that. So another way of thinking about that is, the DPI, right? So still DPI. Okay, instead of storing the key, still the key and value, right? Instead storing the index of the stone here, we store the value here. We store the distance that stone represents. In this case, that's 0, 1, 3, 5, 6, 8, 12, and 17. So this is gonna be the distance for the stone itself. And the value is the same. The value is the same as the previous one. Still the same of the possible jumps. So it's a set. The possible jumps that can reach this like this this like this stone. And the way we're calculating it, we're not going back. So when we calculate the dp, right? When we calculate the dpi, we're not going back to look for the dpi minus 1 or I minus 2. Instead, we'll be going forward. We'll be going forward to dp something like a dpj, where j is greater than I. How, right? That's because at the current dp, right? Assuming, let's say we already have the values of the current dp, which is 0, right? For the 0, we know the length of the 0 is 0, right? And the jump, basically the first dp, the dp0, it has only one element in the set, which is 0. Basically for dp for the first stone, we jump 0, right? And then starting from there, we can calculate. So from 0, we know that the next jump has to be 1, right? Because that's 0, 1, and yeah, 0 and 1. And then how about the second one? And then the next jump will be 1 or 2, right? 0 means nothing. There has to be a jump, otherwise it doesn't make sense, right? Has to be 0, 1 and 2. How about this jump? Still 1, uh, 1, 2, and 3, right? So every time when we see this DPI here, we already we will have the all the possible jumps, right? And then we just get each jump, right? We get each jump of the current DP, and then we just do a small for loop, do a k minus 1 to k plus 1, and then we look forward. We look in the later units. if any j appears, right, and then we just add that jump uh, into this dpj, because that's when we know, okay, we find another possible way to jump into the later stones. And then later on, when we process this dpj, we already have all the jumps possibilities stores in this like set, right? And then in the end, same thing, we just check that for the last stone, for this last stone, how many possible ways we can jump into this. Basically, instead of looking backwards, this time we're looking forward. Since we know how can we jump, what are the possible ways we can jump from the current stone, right? So and okay, let's try to code these things here. Okay, same thing here, right? Uh, and let's get the length of the stones first. And then let's create a DP, right? In this case, the DP will be I'm going to use like a dictionary for this DP instead of a list, because later on we'll be looking for the keys. Uh, we'll be looking for the keys in this dictionary. So in that case, the dictionary is faster than the list. So and the value of the dictionary will be we can initialize it, right? Because we know the key will be all the distance for this stone, right? So the value is going to be stone, right? And how about the value? The value is going to be the set, right? For stone in stones, right? That's how we initialize this DP first. We put all the distance there with the empty set, and then for the DP0, we know, right? There will be only one set, only one element in the set, which is 0, right? So that's why we add 0, because right, and then we just loop the I in range n, right? Because we'll be starting from zero, right? Because we already have the distance, the jump distance for 0. And okay, so let's see. So the next step will be we are at the current stone, and we'll be getting all the possible ways, all the possible jump sizes that can jump to this current stone, right? For I'll do a k in range, right? dp I, right? So for each of these jump stones, right? And and if then we need to have like another small loop here, right? For step, right? For step from k minus 1, right? From in range. So with each of the jump distance, and we'll be doing this k minus 1 to k plus 1, right? So that's why we do a step in range k minus 1 to k plus 2, right? That's the small for loop for each of the k here. And then we do what? So like I said, the step has to be greater than 0, right? So if step is greater than 0, or we can use step and what? And let's do a check, right? Since we only care about the stones here, right? For all the other distances, we don't care. And let's say, hmm, so this is the current, yeah, if the step, uh, That's the step. We can jump. Okay, so and k plus step, right? Because that's the current, that's the previous jump, and that's the next jump we can make based on this k, right? If this thing is in the DP, right? So that means, okay, so the next jump is one of the stones here, right? So we just add, right? We just add these things to that DP's k plus step, right? Since the key is the value of that, right? So we just add that into the jump. It's the step, right? Yeah, because that's the from the current uh the distance of the last jump is k to this step, right? And the next jump, the next step will be one of this, right? So k plus the step will be the next jump that this jump can reach, and the next jump, if it falls, is one of the stones in the later on, then we just add this current step to that stone's like set list, right? And then in the end, we just simply return, right? If the length of the DP uh, stone is the yeah, sorry, the DP of the value of, oh, that's the stones like -1, right? Sorry, the last stones, right? If this DP is greater than 0, right? If this if the last stone, because the key is the stone itself, so we just use that to find uh, the last stones set, right? If the length is greater than 0, then we know we find at least one way of jumping to that last stone, right? I think that should. Okay, let's see for DP. Okay, let's take a look. Yeah, I think here it's not a DP, it's not a I, since we're using the stone as the key. So here should be the stone's uh, I, right? We're using the value of the stone to be the key. Hmm. See. DP. Oh, sorry, it's not. Yeah, it's not range. Yeah, I'm sorry. We are looking at the set here, so we simply get each element in the set, right? Not the range. So just the set itself here, and then each element in the set, and then we just try to get the possible next step from that from the current previous one. Uh, oh, okay, sorry. So here, yeah, I'm sorry. Here it should not be the previous k here. It should be the current stone's distance, right? So that's the yeah. So from the current distance, from the current stones, that's our base basically. That's the base, the distance, and that's the jump step here, right? So we have to use the current stone's distance plus the step, and then we can have the correct next distance. Yeah, sorry about this, all this kind of confusion here. And like I said, so basically, uh, let's take a look at the problem here one more time. So what the key idea here is that instead of using the index, we use the stone distance itself to be the key, and the value will be the set, right? On how many all the possible jump like distances that can be jumped into the current stone. And when every time when we see a new stone, we get all the possible jumps, right? Possible jumps to the current stone, right? For each possible jump, we know with that jump distance, we have three possibilities to jump to the next position, right? That's why we loop from k minus 1 to k plus 2. So for each jump possibilities, we get the new jump, we can next jump, jump step, right? Jump distance, right? We can do this, I think. So the next jump distance will be the current position, right? So since we have I, we know the current distance, right? Let's say for example 4, right? We know the 4 and the next jump step, right here, right? So the current stone 4 plus whatever the jump step is will be the next place it can jump to, and we check. So first, if the jump step has to be greater than 0, otherwise it didn't jump, right? And second, we check if this next jump distance is one of the stones, right? Then we just simply add this jump step, right, to this step distance. It could be duplicate, but since we have a set here, so keep adding the same. If we add a duplicate step here, it doesn't really matter, right? Yeah, every time we see a possible, we see another stones in our predefined DP dictionary, we just add this possible step to this like DP element. In the end, we just check. We check, oh, for the last stone, do we have any possible jumps that can be jumped to this final stone, right? Uh, yeah, I think that's pretty much for this problem. The only the so this the little trick to remember here is instead of looking back like the normal DP problem, this DP problem is looking forward, right? That's the only difference. Cool. Thank you so much for watching the video, guys. I'll be seeing you guys soon.